Okay, we're back. I didn't really mean to hit stop when I was building the models, so that's why this is a fifth segment of the video. Um, anyway, what I drew when I pieced together the geometries around the atoms in ethanol came out something like this. And actually, this is a model of ethanol. And if I turn it the right way relative to the camera, you can kind of see that the model I drew just based on what the VSEPR theory says about those, those central atoms, the carbon, and the oxygen, actually comes out to be pretty accurate. The black atoms are carbons, the white ones are hydrogens, and the red one is an oxygen. And as you can see, that's actually not a bad rendering just based on the VSEPR theory. And you can piece together things like that into information on larger molecules. The next topic is in section 10.5, and that is molecular shape and molecular polarity. The polarity of bonds is pretty easy. Essentially, if you've got a bond that involves two atoms with significantly different electronegativity, then the bond is polar. Pretty simple. But polarity of bonds and polarity of molecules are not the same thing. Okay, so that's easy to tell whether the bond is polar. But the polarity of bonds and the polarity of molecules are not the same thing. So the fact is that the polarity of molecules depends not only on the polarity of the bonds, but how they're arranged around the central atom. So it's not just whether the bonds are polar, it's how they are arranged around the central atom. And that's important because it is entirely possible to have polar bonds in a molecule that are arranged in a way that their polarities cancel each other out. And so that's why we have to consider how they're arranged as well as whether they're polar or not. Or in other words, it also depends on the shape of the molecule. So generally, and these rules of thumb are not universally true, but generally, if you're talking about a diatomic molecule, a diatomic molecule will be nonpolar if the two atoms are have the same or very similar electronegativity. And it'll be polar if they don't. So in the case of diatomic molecules, in other words, what we're saying, for that case, for a diatomic molecule, the polarity of the molecule is the same as the polarity of the bond. But in larger molecules, that is not necessarily the case. And when it is, it's basically a coincidence. Okay, so for larger molecules, if there are no lone pairs on the central atom, and all of the outer atoms are of the same element, the molecule is probably nonpolar. And this is because essentially any polarity in the bonds will likely cancel out due to symmetry. Okay, some examples of situations like that would be, say, CH4, carbon tetrachloride, CCl4, CO2, SF6. These molecules all have a certain symmetry to them that allows the polarity of the bonds to cancel out. So for example, in carbon dioxide, the oxygens are more electronegative than the carbon. And so this oxygen on the right pulls electrons towards itself and makes that end of the molecule partially negative and the carbon partially positive. But the oxygen on the opposite end pulls electrons towards itself with equal vigor or equal strength. And that end of the molecule ends up being partially negative. And the polarity of the two bonds ends up canceling out. So there's a good example of what we're talking about here. Notice the central atom has no lone pairs on it. And the outer atoms are of the same element. And so it fits the bill. Not, like I said, that doesn't always work, 100% of the time, but it's a good rule of thumb. So on the other hand, and remember, I double underlined the and because both of these things have to be true. There have to be no lone pairs on the central atom, and all of the outer atoms have to be the same. Whoops. Then it's probably nonpolar. If either of those things is not true, then it's probably going to be polar. If the central atom, on the other hand, has one or more lone pairs of electrons, or the outer atoms are not all the same, then the molecule is probably polar. And that's because any polarity in the bonds doesn't cancel out because of lack of symmetry. Some examples of this would be ammonia, water, chloroform, and they all basically lack symmetry. For instance, we saw with the VSEPR theory for water, the molecule is bent, and the oxygen pulls electrons in from the hydrogens at the same time and more or less in the same direction. So you end up with one end of the molecule with a partial negative charge and the other end of the molecule with a partial positive charge. You've got separation between the negative, or the center of the negative charge and the center of the positive charge, and that makes this molecule polar. With ammonia, we end up with NH3 being a trigonal pyramid with a lone pair on the central atom. And again, we end up with nitrogen pulling in electrons from the hydrogens and nothing pulling against that. So basically the nitrogen is pulling electrons up from the hydrogens and nothing counteracting that. So the nitrogen end of the molecule is partially negative and the hydrogen end of the molecule is partially positive, and that ends up being a polar molecule too. And polarity of molecules is important because it affects things. Basically, polar and non-polar molecules have different properties. So these would be properties like solubility, for one thing. Like dissolves like is the old saying. So polar compounds tend to dissolve in other polar compounds, whereas non-polar compounds do not dissolve in polar compounds. Non-polar compounds would dissolve in other non-polar compounds. So oil and water, they don't mix because water is polar and oil is not polar. Melting point is affected by polarity. Boiling point is affected by polarity. Density is affected by polarity, and a whole bunch of other things. Okay, there is a section on page 414 about vector addition, which basically shows you how to determine, basically it's this kind of thing, showing you how to determine if a molecule is polar or nonpolar based on the way the bonds are arranged and the electronegativity differences between the atoms in the bonds. You can look that over. It's not something I think you really need to know in great detail, but you should probably be at least familiar with it so that you can determine whether molecules are polar or nonpolar based on their VSE, based on their Lewis structures and the VSEPR theory. Okay, so I'm going to leave it there for this lecture. We'll get on with that next time. We'll carry on. And that's the end of 10.5.